some work that we have done with our PhD student here at IIT Delhi. So I'll start presenting. So is this visible? Is my screen visible?
Yes, sir.
Yeah. Okay. So this presentation is specifically on millimeter wave antennas for body area networks, or BAN as they are called. So we'll start with some introduction to what are body area networks, where are they used, what is the advantage of using millimeter wave frequencies. So the specific frequency in the millimeter wave range that I'll be talking about is 60 gigahertz. So the band of 60 gigahertz with a bandwidth of 7 gigahertz is unlicensed. So there is where we have been working in this area. So I'll discuss different types of antennas, different types of scenarios, and some preliminary results of the same. So a small introduction. W-band, as we most of us know, is a multi-tier network. It is used for medical purposes a lot. So in this, small biosensors can be put around or implemented inside the human body. So you can put the biosensors on your wrist or on your leg, around your chest, or they can as well be implemented in the human body. This implemented in the human body is not yet taken. It has not yet taken off, but biosensors which are worn around the body have certainly been used in a lot of applications. So these devices, biosensors, they essentially monitor and record human health parameters. So different parameters. In the first session, we saw the remote sensing of human vital sign detection, where there was no sensor of the human body. Right. So in this case, we'll put a sensor in the form of an antenna on the human body and try and record various health parameters. So the focus in this presentation will not be on actual measurement of the parameters, human health parameters, but it will be more on the antennas that are required for such an application. So in this body area network case, the sensor nodes are connected with a sync node, which are connected to the medical server through a PDA or a laptop. Medical server, on the other hand, at remote location, receives data which contains patient's daily reports and his vitals. So, the sensors will be on your body. You will communicate through those sensors to a PDA or a laptop. It could be your mobile handset as well. And that mobile handset will transmit the signals to the medical servers, and which will be accessible to doctors. Right? So this will have patient's daily reports and his vitals in critical cases. Body area networks, apart from medical applications, can also be implemented for military and sports training. So there have been a lot of news that they are being used in military and sports training. Then interactive gaming and information sharing. So there are a lot of new applications that are coming up. I think in some of the applications of variable things, biosensors, were discussed by Dr. Munir in his inaugural address. Right? So those applications include sports training. Right? So you could have something fitted in your shoes, or you could have something fitted on your leg to know certain parameters, or you could monitor your heart rate while you're running and so on. So these things, these applications are coming up, and there's a huge market for this as well. But the critical part here is the antenna, because antenna works as a sensor, right, which will take certain information from body and then communicate it in a useful manner with the medical servers. So that antenna is very critical, as I was mentioning initially. variable antennas, right, are a very like problematic case. It is not very easy to design a simple antenna and then put it on your body, and then it will not work as per your requirements. So there are some special techniques, some special antennas that are developed, which I'll discuss in the course of this presentation. So there are two basic scenarios for body-centric communications. One is on-body to off-body propagation, so which you can see here. So this dots that are seen here, so these are basically biosensors or antennas, you can say. So this is on-body. So on-body to off-body. So this has to communicate with a personal device here. And then over internet, they will go to a medical server. So on-body to off-body. This is one communication link that comes into picture. And so this, in this case, the propagation is usually perpendicular to the body. And what we require is a broadside pattern. So people with antenna background will understand what a broadside pattern looks like. And also the challenge is minimum exposure towards the body. Typically the antenna will radiate in both the direction, forward direction as well as backward direction. So an antenna which is communicating to a personal device, right, will also send some energy in the body. Right? So your body will also be exposed to electromagnetic energy. So therefore we should have an antenna which will have minimum, which will give minimum exposure towards the body, which will radiate minimum amount of energy towards the body. The second scenario is what is known as on-body propagation. The on-body propagation is these nodes, these biosensors, they communicate with each other. Let's say, for example, this antenna here at the heart will communicate one at the on the head, right, or it will communicate to the antenna on the hand, and so on, to perform different functions. Right? So this is another scenario. So the two scenarios are, one is on-body to off-body communication, and other is on-body communication. So this antenna can connect to another antenna or another sensor on this body, on the body itself. So for on-body propagation, the pattern should be tangential to the body, or it should be an end-fire pattern. Right? Because broadside pattern means normal to the body. Right? I just turn on my video. Yeah. Right. So broadside. So for those people who do not have background in antennas, broadside is, if this is the antenna, broadside would mean normal to the antenna surface. Right. End fire is along the antenna surface. So for off-body communication, because this is an antenna, it has to communicate with a personal device, right, or a laptop. So it will communicate in a broadside direction. Whereas if there's an antenna placed, let's say on my wrist, right, and if it has to communicate to an antenna placed on my head, it will require a inline propagation or end fire propagation. So pattern should be tangential to the body. So these are the two main things: broadside pattern requirement with minimum exposure to the body, and in this case, it is pattern should be tangential to the body on an end fire pattern case. So these are the two things that one must remember when discussing or when designing antennas for body area communication or body area networks. So we have done work on these antennas at 60 gigahertz. So some introduction to 60 gigahertz propagation. So the first wireless communication using 60 gigahertz carrier waves was studied by Sir J.C. Bose in the year 1895. So he is, Sir J.C. Bose is called as the father of millimeter wave communication. This band is the ISM band, industrial, scientific and medical band, at 60 gigahertz is designated for this communication. And there's a bandwidth, unlicensed bandwidth of 7 gigahertz at this in this band, 60 gigahertz band. So you can imagine 7 gigahertz of bandwidth. It's a huge bandwidth. So obviously your data rates and other things will be very good. So these are the table shows the unlicensed bands in the 60 gigahertz for different countries. So USA it is 57 to 64 gigahertz, Canada is same, Japan is 59 to 66, European Union is 57 to 66, Australia is 59.4 to 62.9, South Korea is again 57 to 64, and India would generally follow the US or the European model. So what the researchers, what they do, who work in millimeter waves, so we generally take from 57 to 65 gigahertz, 64, 65 gigahertz. So that is where we do all our designs, not only antenna, but other circuits as well. So what are the benefits of 60 gigahertz? As you can imagine, in normal cases, the size of the antenna is approximately half wavelength at the operating frequency. So when we go higher up in frequency, the wavelength decreases. As a result, the size of the antenna also decreases. So the spectrum, moreover, what has happened is the spectrum below 10 gigahertz is already crowded. As we all know, there are a lot of applications in the sub 6 gigahertz region. Mostly it is sub 6 gigahertz. So there are a lot of applications. There is Wi-Fi, there is mobile, there is WiMAX bands, RFID is there, you have WLAN, everything is there in that sub 6 gigahertz band. So the spectrum is actually very crowded now. Secondly, as I mentioned, the antenna size is much smaller at 60 gigahertz. So it saves a lot of space. Say, for example, if you were to wear a 2.4 gigahertz antenna on your, let's say, arm, like it would be a huge antenna. 2.4 gigahertz antenna will be a very large antenna. But if it were a 60 gigahertz antenna, it will be a very small antenna which can be easily fitted. Nobody will even notice it. Now, since the bandwidth is very large, 7 gigahertz bandwidth, so your data rates are very high, then there is less interference between co-located band users at 60 gigahertz compared to 2.4 gigahertz. So 2.4 gigahertz, there will be a lot of interference. Let's say, assume that I have a 2.4 gigahertz antenna on my arm, somebody else has 2.4 gigahertz antenna on his arm, and there will be a lot of interference. So at 60 gigahertz, because the communication distance is not very large, these are for short range communication, the interference between co-located band users will be much smaller. And then this is an unlicensed band, and then higher signal attenuation. So this is one of the drawbacks. You cannot communicate at 60 gigahertz to, let's say, 5 kilometer or 10 kilometer. It is a very short range communication system. At very short ranges, maximum you can go is 100 meters, unless you apply amplifiers and other things, of course. But 100 meters, 10 meters is what we are looking at. Now, another concept that comes into picture is what are known as phantoms. Right? So these phantoms are basically used for experimental purposes. You cannot do experiments on human body directly. You cannot do experiments on animals. So what is done is these phantoms are used to mimic human body parameters. Right? So there are some privacy issues when it comes to experimentation in all the fields, not only in antennas. So what is done is phantoms are created. So you basically mimic the human body parameters using a artificial substance and shape it into the form of a human body so that you can do the experiments. These phantoms are needed to estimate the effect of human body on the antenna parameters and wave propagation. Right. So instead of using the actual body, we use these phantoms so that we can estimate what will happen with the human body. These phantoms are classified either as solids, liquids, or semi-solids. So all forms of phantoms are available. It is not necessary that we buy these phantoms from market. You can as well do your own phantom, which will basically mimic the human body parameters. So it will take into account the effect of the skin. It will take into account the effect of tissues, bones, blood, and so on. So liquid phantoms are used up to 6 gigahertz for handheld mobile devices. Then the semi-solid phantoms and solid phantoms, they do not require container and can be used at millimeter waves. So lower frequencies, generally liquid phantoms are used. But for higher frequencies, you either use a semi-solid phantom or a solid phantom. So the semi-solid phantom composition to mimic skin properties at 60 gigahertz is given in this table. So these are the components. So deionized water is 81%. So this determines the dispersion of the phantom. Then a polyethylene powder, 16%. This is used to decrease the phantom permittivity. Then agar, 1%. This is to retain the shape of the body. Then TX151, there's material called TX151. This is used in a small percentage to increase the viscosity. And sodium azide is used as a preservative. So these are the typical things, typical materials that are used to make a semi-solid phantom. It is not a completely solid phantom, but a semi-solid phantom. So the net property, so when we mix all of this in the given proportions, net material that we will get, it will have properties very close to the human body properties. So semi-solid skin equivalent phantom of an arm and an hand. Right? So this is how the semi-solid phantom will look. You can actually shape it in the. So this is like a, you do a plaster to your hand with that material. Right? Remove that plaster and it will work as a phantom. Right? The skin permittivity. So when we say the parameters should be similar to human body parameters, so one of the first thing that comes to mind is the permittivity. And so this skin permittivity you can describe using Device equation. So this is epsilon equal to epsilon at infinity plus epsilon static ES minus epsilon infinity by 1 plus j omega tau. So where the static permittivity is 37.2, the optical permittivity is 3, that is epsilon infinity is 3.88, and relaxation time is in picoseconds. So this is how we can calculate the skin permittivity at any given frequency. Omega comes into picture, right? At different frequencies, the permittivity value will be different. So state of antennas reported at 60 gigahertz for this application. So first one, the figure on the top shows a 4-element printed array on RT-derived substrate with gain about 11.8 dBi and bandwidth of 6 gigahertz. So you can see here 4 elements fed by there's a power divider that is there to feed power to all the 4 antennas, and then you have a microstrip line. Okay. So this is put on a phantom. So if this word is clear to you, this is a phantom. So this is put on a phantom to do the experiments. Then second type of antenna that is used is a Yagi-Uda antenna using 4-way power divider on RT-derived substrate. So this RT-derived is a dielectric material from a company called Rogers. So of thickness 0.127. So the gain, because it is a Yagi-Uda antenna array, the gain is about 15 dBi and bandwidth is about 5 gigahertz. So the substrate, you can see the antenna is printed on a very thin substrate, 0.127 mm, and that is 127 microns. Right? So this is very small, small substrate. So antenna, you can see this is the field line. The power is divided into 2 parts, which is further divided into 2 each. So we have 4 elements. And since it is a Yagi-Uda, you have reflectors. So these vertical lines are reflectors, whereas these are directors. Right. Then we have H-plane SIW. SIW is substrate integrated waveguide. So there's or you can, if you do not know what SIW or substrate integrated waveguide is, you can think of this as a dielectric loaded waveguide. So usually you have a waveguide, there's air inside it, right? If you put in dielectric, it will be similar to this substrate integrated waveguide. So it is designed on a substrate of thickness 0.787, gain is about 6.6 dBi, and bandwidth is 6.1 gigahertz. So these are some of the antennas reported at 60 gigahertz. Then there is a textile antenna. I was mentioning that there are the antennas which are fabricated on the material, the fabric itself. Right? If you wear a T-shirt, there will be an antenna embedded inside that T-shirt. So this is a textile antenna fabricated on a cotton fabric. So this is a Yagi-Uda antenna on cotton fabric, thickness 0.2 mm. So gain about 9.2 dBi and bandwidth is 7 gigahertz. So this is, again, you can see there is a cotton fabric. So you have printed the antenna on a cotton fabric. Then you have textile antenna. So you can see the antenna here. There's a phantom, right, and there's a connector here. So this is a four element array on 0.2 mm fabric. Gain of about 8 dBi and bandwidth of about 7 gigahertz is achieved in this. So this is textile antenna, one type of textile antenna, Yagi-Uda type of textile antenna. This is a 4-element patch array on a textile, on a fabric again. So once we do this, so the care should be taken. Say for example, this is you can see this is a very small antenna, there's a fabric. Now when we wear this fabric, right, if I make a shirt out of this fabric, right, so what will happen? This antenna will bend. Right? So one has to take care that even if the antenna bends, right, or there are some other deformations in the fabric, the antenna should work nicely. So that is the main challenge that one has. Then there is an antenna, very complicated antenna, fabricated on FR4 substrate. I think this is all of you are familiar with FR4 substrate. So this is again 0.127 mm thick with center-fed octagonal plates and 8 Yagi-Uda antennas. So this is a center plate, octagonal center plate. So feeding is through this, and then further we have this Yagi-Uda type of directors. So the gain achieved is much smaller here, 2.86 dBi. Although the antenna is complicated, the gain is not much, 2.86 dBi. Then there's an antenna printed on a flexible substrate with a bandwidth of 9.8 gigahertz and a gain of 10.6 dBi. So there are a couple of designs that I'm presenting, which are already reported. So let us now look at the requirements as far as the antenna is concerned for applications in body area networks. First is it should be low profile, small in size, so they're used alternatively, low in profile or small in size. It should be lightweight. You don't want to carry a very heavy thing on your arms or on your shoulders or on your chest. They should be conformal to the body. They should take the shape of the body. I cannot have, let's say, the antennas that are used in your Wi-Fi routers. Okay? I cannot put a aerial coming out of my hand, right, or aerial coming out of my brain, my head. Okay? So they should be, the antenna should be conformal. They should take the shape of the body part where it is mounted, and it should be a fairly high gain antenna. Because at 60 gigahertz, as I said, the range is very small. Okay? So in order to get more range, the only way is to increase the power from the antenna, that is, increase the gain of the antenna. So first part we did was, so this is modification of the previously reported antennas. So this is called as a end-fire antennas for on-body links. So on-body links are from one part of the body to the other part of the body. So this is a simple design. So what we have is, so these two parts that are shown. So this is the top side. The black color indicates conductor. So this black is a conductor, whereas this blue color is the dielectric. Right? So on a dielectric, like a PCB board, right, on one side you have this pattern, on the other side you have this pattern. So this large dark region that you see is the ground plane. So on one side, so you have this arm here, this is the second arm. So this works as a dipole antenna. So this is your ground plane, and this works as a dipole antenna with directors in front, so as to increase the gain. So if you remember, I told that for on-body links, we need an end-fire antenna. Right? So this antenna will radiate in that direction. It will radiate in that direction. It won't radiate perpendicular to the antenna. Right? So this is the fabricated thing. So what we see here is again similar thing. On top, you see a line. Now there are different thicknesses. If you see the line thickness here is different from here and it is different from here. So this is essentially to match the impedance. So the antenna itself will have a certain input impedance. So you have to match the input impedance of the antenna to that of the feed line. As a result, what you have is we have a matching line in between. So this line, referred to as matching line, transforms the impedance, input impedance of the antenna to that of the feed line. So let's say typically the input feed line is 50 ohms, and let's say the antenna input impedance is 100 ohms. Right? So this matching line is usually a quarter wavelength long, right? And the impedance is square root of 50 into 100. So that is the impedance. So as the impedance increases, the width of the line decreases. Right? So this feed line is wide as compared to these two lines. So the impedance of a wider line will be less as compared to impedance of a narrower line. And then this is the back side. So this is basically off-center director pair. So this directors, right, they're off-center. They are not in the center. You can see a cut here in between. And this gives us a very high gain configuration. Right? So we'll see the results here. Okay. So this figure shows electric field distribution, E field distribution with and without directors. Okay. So the figure on the right that I'm showing with the mouse here is without the directors. If there are no directors, what happens is the beam is quite broad. Beam is broad, it also means the gain is small. Okay. Now the figure on the left shows antenna with directors. Okay. So as you can see, there is this red color here indicates more field. Okay. You can read the scale here. The red color indicates more field. Blue color indicates less field. So what we see here is without the directors, there is very less field, right? So this green color approximately here. Whereas with directors, you'll see that there is a lot of concentration of energy, right? As a result, what happens? Your gain increases. Right? The energy is focused, right, in a particular direction. As a result, since the energy is focused in a particular direction, the gain increases. So from the E field, it is concluded that two spatially placed directors are excited by the single dipole. With the directors, the beam is narrower in E plane and it results in a high gain. The beam narrows high gain. You can see the spread here. And the spread is wider here, here it is narrower. So these are simulated and measured return loss. So there's a term called return loss and also known as S11. So this basically indicates how well the antenna is matched with the feeding line. Because for the antenna, if we have to supply power, there has to be impedance matching. Right? And this if the impedance matching is good, then maximum power is transformed from the source to the antenna. So antenna can radiate more power. If there is impedance mismatch, most of the power will be reflected. Right? So this parameter S11 or return loss indicates that impedance matching. So if this S11 is less than minus 10 dB, right? If it is less than minus 10 dB, it means there is a good impedance matching. So there are three curves here. One red one shows the simulated curve. And look at the frequency range here. It is from 55 to 65 gigahertz. Right? So the red curve indicates the simulated return loss, simulated impedance matching. The blue curve, the black curve indicates measured without body. So black curve indicates the measurement without the body, and blue curve indicates measurements with body. So if the antenna is put on body, okay, how does the impedance matching change? So what we see is when the antenna is put on the body, there is no change in the impedance matching. You will get similar band, right, of frequencies below minus 10 dB, even with body. Right. What also we should notice here is there is slight change in the frequency. Right? There is slight change in the frequency, mainly because, as you can appreciate, this is a double-sided PCB. So this is on one side of the PCB, this is on the other side of the PCB. So while fabrication, And there are two steps involved. This is a two-step fabrication. First, you print this, and then you print this. Now, the alignment of these top and bottom is very important. If there is slight misalignment, your frequencies will be off. So that is what has happened here. There is slight misalignment of the top and bottom, and as a result, the frequency has slightly shifted. But you're still within the band. You're still getting within the band. So I'll read out these things here. So there's a shift in the measured and simulated results but the profile of the measured results is similar to simulated. So the profile wise, it is similar. There is 4 gigahertz impedance bandwidth is achieved. So structure is very simple, and you get about 4 gigahertz of impedance bandwidth. End fire antenna placed over the human body with a gap of 5 millimeters. So from the body, the gap is 5 millimeters, and that is how the measurements are done, the blue curve here. So you still get equivalent impedance matching as without the body. And we see that the reflection coefficient of the antenna is not much affected. Now, these are radiation patterns in 2 planes, E plane and H plane. So these radiation patterns are at 57 gigahertz. So there is, when we talk about this high frequencies, it is very difficult to do any measurement. You require a special type of connectors which will work at that frequency. Normally, the connector that we get in the market in India, they work only up to 6-7 gigahertz. Right? Beyond that, you have to import connectors. So this was done. I'll show you a figure. You can see this connector here. Right? So this is a southwest end launch connector, right? And one connector costs about $400. And this works up to 67 gigahertz, and it costs about $400. So that's like one connector is about 30,000 rupees. So it is very expensive at high frequencies. These are the radiation patterns. So gain in both the cases is better than 9 dBi for the entire band. So we are seeing that the bandwidth is about 4 gigahertz. So the patterns were plotted at different frequencies in that band where the impedance matching was good, and we see that the gain is better than 9 dBi. So this is for E plane pattern. So you can see that there is large concentration of power in a small beam. Likewise for H plane. So for H plane, you get slightly there is kind of power going in the other directions as well, but this can be taken care by putting in appropriate reflectors so that the entire power goes in the forward, the end fire direction. Right. Then there is a modification of that antenna was done because you want to cover different nodes, right? So on-body communication. So modification of that was done. So this is the back side of the antenna. So you can see that there are 3 antennas, such antennas, right? And this is the front side. So this is your ground plane. So 3 such antennas were done together. So the figure is as shown here. They are connected by 3 connectors. So the cost of this antenna, along with the connectors itself, will be more than 90,000 rupees because each connector is about 30,000 rupees. And so the cost of this antenna, the substrate, the fabrication and all, it will be more than 90,000 rupees to test such an antenna. And of course, in the practical systems, you don't require these connectors. These connectors are used only for doing measurements in the lab. For practical application, if you say this connector is 30,000 rupees, nobody will buy that system. So in practical case, you don't really require this connector, right? So this is off-center director pair, similar thing. So what happens is, because we have now 3 antennas, so this antenna will radiate in this direction, this antenna will radiate on the top, this antenna will radiate to the right. So we have left, top and the right, 3 directions being covered. So that is what is shown here. If it is put on human body, it will radiate left, right and along the center line. So the field distribution with and without directors is shown. So what you see here is with the directors, there is a lot of concentration like before. of fields. As a result, you get narrow beams. So this is one case. This is the center antenna is excited. Here, the left antenna is excited, right? And this is the case with no directors. So there is very wide beam happening here. Whereas in this case, there is narrow beam. So if the center antenna is excited, the power will be radiated along this direction. If the left antenna is radiated, the power will be radiated along left direction. There will be no power along the other two directions. Now, what is also important to note here is there are three lines. This is line for the left antenna. This is line for the center antenna. This is line, field line for the right antenna. Now, when I excite one of these antennas, the other two antennas should not be coupled. Right? Now, what we see here is if I excite the center antenna, this red things that you see here, right? So this antennas are also getting excited to some extent. Right? So there is power, there is coupling happening to some extent, and that coupling can be reduced by what are known as electromagnetic band gap structures. Right? So those are also used a lot in our lab. So we use electromagnetic band gap structures to reduce this coupling, because if you want this antenna to be, the center antenna to be excited, only that should be excited. Other two should not be excited. Right? So in this case, the beam is more confined with off-center director pair. There is coupling due to closely spaced field lines. If you look at the figure here, the field lines are very closely spaced. Right? As a result, there is small amount of coupling that is happening there. And coupling from orthogonally placed elements is less. So if I excite this element, the element on the left, the element on the right will not be excited much. You can see that, look at the color, red indicates maximum. Right. So when the center is excited, there is coupling happening to the left as well as to the right. When the left is excited, there is coupling happening only in the center. Right means there is very, very weak coupling. So these are the return loss plots. So there are a lot of plots here, simulated as well as measured for the three antennas. So what we see here is the measured impedance bandwidth for the center port, the left port, that is port 2, and the right port, port 3. So when I say port 1, port 2, port 3, we should immediately be looking at S11, S22, and S33 respectively. Right, so S11 center port, this is the curve. S22 red curve. S33 blue curve. Right, so what we see is the bandwidth is very similar. And so these are simulated and these are measured. So as I said, there's small change in the simulated and the measured because of the alignment issues. So the bandwidths are from 55 to 60 gigahertz, 55.2 to 60.9, and 55.5 to 60. So in all the cases, you get bandwidths better than 5 gigahertz. This is the mutual coupling. So it is also called as isolation. So isolation between the antenna elements is better than minus 15 dB for all three elements in the impedance bandwidth range. So you can see that in the impedance bandwidth range, that is up to 60, 61 gigahertz, the coupling, right, is less than 15 dB. So if I draw a line at 15 dB, it is less. Isolation is good because the antennas are placed orthogonally. Because one antenna is pointing in that direction, other is pointing in this direction, the third one is pointing in that direction. So therefore, the isolation is good. These are the radiation patterns for three antennas. So one is center excited, then left excited, and right excited. So you can see that there are three patterns. This is center excited, the blue curve shows left excited, and the yellow curve, the mustard color, shows right excited. So we get patterns in three different directions. Right? So one single antenna can communicate with three different nodes on the body. So this is the E-plane pattern is plotted at 58 gigahertz. So E-plane pattern, it is said that it is XY plane. E-plane pattern is your XY plane. That is perpendicular to the antenna. The beam directions are 8 degrees, 87 degrees, and 278 degrees. So distinctly different directions. Gain is better than 9.2 dBi for all the three elements, and this antenna can be used to communicate on-body devices in three different directions. Let's say if you have an antenna placed, this antenna placed on heart, it can communicate to your legs, it can communicate to your right arm, and it can also communicate to your right arm. Same antenna structure, but three different feeds. It can communicate to different points on the body. Then this is a switch beam antenna configuration. So here the beam is switched. So instead of having the directors right, parallel to this excited element, the directors are now at an angle. If you see the previous figure, so these directors, they were parallel to this excited element. Now they are tilted. There are two ports used, port 1 and port 2. The directors are tilted. So this is your S11 and S21. So S11, that is impedance bandwidth, is large, and S21 indicates the mutual coupling, which is better than minus 20 dB, because the ports are sufficiently far apart and there is a distance between the feed lines. So your the isolation is better than minus 20 dB here. So impedance bandwidth is 55.6 to 64 gigahertz, and isolation is better than 20 dB in the entire band of frequencies. Here, I just read this thing as well. So this is the Yagi antenna, modified Yagi antenna. The second arm of the dipole is 90 degree, is rotated to 90 degree, and is shared for both antenna element structures. Right. So second arm, so this is the one arm, second arm is tilted. So what we see is the rotation is 90 degrees. So as a result, they will combine. And so this is a tilted beam configuration. So we look at the beam now. So in this case, we see normalized radiation pattern. So red curve is excitation 1, and the dotted blue curve is excitation 2. So what we see is this antenna radiates along plus 60 degrees, the other antenna radiates along minus 60 degrees, or 300 degrees. So you get two separate beams here. So the 3D plot is as shown here. One antenna is radiating along this direction. Look at the direction of the red color here. And the other antenna is radiating along the other direction. And this is excitation 1. This is excitation 2. So the antennas are radiating along different directions. Now, third one is a lens antenna for off-body lens. Right? So on-body, so the antenna is on-body, and then it has to communicate with the off-body. So this is called the lens antenna. So this lens, as you know, at optical frequencies, lens is used to collimate the beam. Right? So there is sunlight, let's say, coming from the top side. We use a lens. What will happen? The lens will focus the sun's energy at a single point. Right? So the lens is used to focus the energy. Similarly, at microwave frequencies, we can use a lens. So this is a dielectric lens that is used. You can see here. And this is a fabricated lens. This is the actual lens. So this is used on top of a simple patch antenna. You can see here, there is a patch antenna here. Then there is gap, and then there is lens here. Okay. So this lens is used. So there is proper designing of this lens done. So this lens is used to focus energies at a particular point. Because at 60 gigahertz, the communication range is very small. So we use lens to focus the power in a particular direction so that the gain increases, and as a result, your read range also increases. So this is the plot for impedance bandwidth. So we can see that there is impedance bandwidth from about 58 gigahertz to 60 gigahertz. So different experiments are done, deviation of the lens from the antenna. So this black patch here shows patch antenna, and this is an off-center patch antenna. So if the lens is exactly above the patch, or it is at an angle from the patch. So different experiments were done. And then what is done is, the earlier configuration of 3 patches, right? So similar configuration is here. We have 3 patches, 3 different field lines, right? And there are 3 patch antennas on top. So these patch antennas, so this is left patch, this is right patch, and the center patch. And these are terminations on the 2 sides. So this antenna, on top of this, there is a lens placed. Lens I had shown in the earlier film. So this red color tom that you see, this is a lens. And there's a proper design of this lens. So this is a 3D printed lens. So we have a 3D printer which will print this lens. So instead of fabricating it separately or taking a semi-spherical shape of that material and then cutting a window, instead of that, what we have done is we have 3D printed this lens. So that 3D printed lens is put on the top here. So antenna substrate is a 5 mil substrate. 1 mil is 25 micron. So 5 mil is roughly 0.127 millimeters. The minimum feature dimension is 0.1 mm, and it is fabricated using conventional lithography. So the antenna dimensions, since the frequency is 60 gigahertz, the dimensions will be very small. So the minimum dimension is 0.1 mm, that is 100 microns. This is fabricated in our lab. Then lens is fabricated using 3D printed based on FDM using PLA as a material. So this is a standard printing material, PLA. A lot of things can be printed, right? So for people who are not aware of 3D printing, so it is like your normal printer, right? Office printer prints in 2D, right? In 2 dimensions. Now this is the 3D printing, so you can as well print in the 3rd dimension. So there is a XYZ arrangement in which this melted paste of the material will be placed, and you program it so that it takes a particular shape. So this is a patch without lens. So again, the beam is very broad, as you can see. This is left patch with lens. So the energy is focused along this direction. This is center patch with lens. Energy is focused. Look at the bright color here. Here as well. Look at the bright color. So the bright color is spread across. Here it is concentrated. Likewise, this is for the right patch. So it is focused on this. So we get 3 different directions. So lens, what does the lens do? Lens confines the beam and thus increases the gain of the antenna. Then beam direction changes with switching the antenna elements. You can either excite the left element or the center element or the right element. So accordingly, your beam will tilt this way, center, or that way. So this is antenna over the body, so it is placed over a phantom, and S parameters are checked. So what you see here is S parameters in free space and S parameters over a phantom. So as you can see, there is not much change in the antenna parameters, at least impedance bandwidth parameters, even if it is placed on a human body. These are the complex permittivity of the flat skein. Right? So the real part is shown by this black line, and blue line shows the imaginary part, epsilon prime and epsilon double prime. So it varies with frequency. And this is the radiation pattern. So blue, this blue curve indicates free space for the patch antenna. Green indicates free space for the left patch. The red one indicates phantom with center patch. And the black one, this is below this blue one, is phantom center patch. So this basically with phantom and without phantom as well. So EM simulation is done to check the antenna performance. Flat skein is used in simulation, as the EM at 60 gigahertz won't penetrate much inside the skein. So the advantage with 60 gigahertz is the energy won't penetrate too much inside the skein. So it is only at the skein level. Right? So therefore, it is the parameters of the skein were only taken into account. The parameters of tissues and other things were not considered. The gap between the antenna and the flat skein is kept at 1 mm. Right? You may have some, this gap is variable gap. Right? So in the experiments, we have done it at 1 mm. And what is seen is not much variation is observed in S parameters and the main beam radiation, as it is evident that the antenna is radiating in broadside direction. So the antenna is radiating in the normal direction to the plane of the antenna. So these are measured and simulated scattering parameters S11, S22, S33, as well as the mutual coupling S21, S32, and so on. And so what we see is they are experimental and measured, simulated and measured values. They match nicely. So measured results are in general agreement with the simulated ones. The impedance bandwidth that we get is around 4 gigahertz, and there is isolation between the antenna element, which is better than 22 dB. So these four curves you should see. So the isolation is better than 22 dBs. So which is good, because you don't want the antennas to communicate with each other. It has to communicate with the intended antenna. Then these are the radiation patterns. As you would expect, there are three different patterns. So the center patch is the black curve, left patch is the blue curve, right patch is the red curve. So you get three different angles, the radiation at three different angles. So even if the off-body device is slightly off here or there, it is still covered because of these three antennas radiation pattern. Gain plot is shown here. So gain is about 10 dBi for all the cases. So center patch measured, left patch measured, center patch simulated, left patch simulated. So the gain, you'll see that it is all above 10 gigahertz in the entire frequency band, 56 to 60 gigahertz, right? And it matches quite closely with the simulated one. The green curve and this purple curve here, they show the simulated ones, whereas the black and blue shows the measured ones. So there is good matching between the measured and simulated. What is also important is these two patterns. The pattern on the left side is taken at 58 gigahertz, whereas the pattern on the right is taken at 60 gigahertz. So just to see that the patterns are consistent over the band of the frequency. Then we have on-body, off-body path gain measurements. So basically you put the dielectric lens antenna on the body, and then we have an open-ended waveguide working at 60 gigahertz off-body. So these are measured using VNA. So this VNA was up to 67 gigahertz. Distance between the human body and the receiver antenna is kept as D. So what is seen is this is path gain versus frequency. So antenna is fixed over the body. There's a difference between the path gain observed with and without body, and this may be due to misalignment. As you can see, there's small difference here. Okay, so without body it is slightly higher, with body it is slightly lower. So this may be because of slight misalignment. Path gain is better than minus 45 dB for the entire band for a distance of 330 millimeters, that is 33 centimeters. So as I said, this is very short distance communication. So we have kept the distance as 33 meters, and we see that the path gain is sufficiently good. And with body and without body, there is not much deterioration in the path gain. Then there were measurements. So there was a question in the first session, right, as to what was the sensor used to, sense the heartbeat movement and all. So in the first part, the experiment that we did in the first session talk, there was nothing placed on the human heart. There were two antennas transmitting and receiving in the radar, and that's how we were measuring the heartbeat. So what is done in this case is the antenna on the body, it is used to capture the heartbeats. And so this antenna is put on the body, and then there is an external node. So there is an external antenna used, which are interconnected to a vector network analyzer. So you can see here, there is an antenna on the body placed at the heart, and this is a receiver antenna here. Right. So you can see the arrangement front side. So there is an antenna placed on the heart. So this is used for vital sign detection now. So instead of using two horn antennas, right, and using the Doppler radar kind of arrangement, here what we are doing is we are keeping the antenna on the body. Right. So it will pick up the changes in the chest movement and then communicate it with this particular antenna. So the central node over the body is connected with an external node to communicate with the external world. Central node is placed over the chest, and due to the chest movement, the variation is observed in the transmitted signal. Right? Because of the chest movement, there is a variation in the transmitted signals. This variation is used to estimate the human vital information, that is respiration rate and the heartbeats. A continuous wave signal is transmitted for time of 15 seconds at 60 gigahertz. And so 15 seconds, for 15 seconds, there is continuous transmission, and we detect the vital signs, the respiration rate and the heartbeat. So again, similar figure that we saw earlier. So this is the spectrum of the received signal. This is spectrum for the respiration signal. And this is spectrum for the heartbeat signal. The respiration signal is you get at a lower frequency, whereas this is slightly higher frequency. Then waveguide is used over the body. So WR19 is placed over the body as a central node. Reference signal is measured using the path loss between the two antennas without human body. The estimated respiration rates are 0.26 Hertz and heart rate is 1.6 Hertz. And so these values, if we go back, so these were 0.2 Hertz and this was 1.2 Hertz or 3.4 Hertz type of this thing, and this was 1.2 Hertz. We're getting quite close to that rate, that heart rates and the respiration rate with this new antenna. So this was using waveguide over the body, and this one is using the integrated patch antenna. Again, you can see that we can detect the respiration signal as well as the heartbeat signal. The signal strength is more and can be easily used over the body. The estimated respiration rate is 0.33 Hertz and heart rate is 1.26 Hertz. So we are able to figure out, right, the heart rate as well as the respiration rate. So the difference between the earlier case, the first presentation before lunch, was that there was no node on the body. The body was under the debris, and we were to detect if there is a heart signal. So that we could do. Now in this case, this is, this can be used for continuous monitoring. So for example, if the body is not under debris, it is, you just put the antenna there and there is a node, external node. So the antenna, based on the chest movement, right, it will communicate with the off-body link, off-body or the laptop or your mobile handset. It will communicate, and so that's how we have got the estimated respiration rate at 0.33 Hertz and heart rate at 1.26 Hertz. Now this is another interesting thing. This is for cavity-based multi-beam antenna for external nodes. So as the name suggests, it is a cavity and it can communicate. So it can have multi-beam antennas. I'll show the figure directly. So it is this. So we have a cavity here. As you can see in this case, there's a cavity inside this. So this is one part of the cavity. This is other part of the cavity. And the holes that you see, these are for screwing fitting them together with a screw. So these are put on top of one another, and then from one side, let's say from this side, you put in the signal. There's a groove here, and then there are three parts. So these three parts will have three different patterns. So that is the idea here. So what we see here is we have TM21 mode is excited in a cylindrical structure. Incoming wave into three different directions is divided into three different directions and radiated with the help of openings. The lens is further integrated. So this lens that we saw earlier to confine the beam and thus enhance the gain of the antenna. So this is the electrical field distribution of cylindrical cavity in eigen mode analysis. This is the electric field distribution. So we have one as the input. So let's say the way signal is coming from below, it goes to left, it goes to right, and it goes to front left. So it is divided. And this is your lens structure that is used to increase the gain of the antenna. So this antenna is fabricated using metal with help of machining. It is fabricated in two pieces and joined together with the help of screw. So this is one piece, this is the other piece. The structure includes a rectangular flange used to attach a waveguide adapter for feeding. So there is a rectangular flange here. So this is a rectangular flange so that we can connect a waveguide for feeding here. The antenna structure includes both feeding structure and cylindrical structure to bifurcate incoming waves. So there is a structure here. You can see this more clearly. So there is a cylindrical structure here so that the waves are bifurcated. So this work is still going on. So this is S parameter without lens integration. So what we see is we get a this is simulated one. We get a narrow band here. So as I said, this work is still going on, but I thought I present it so that you can pick up ideas, and in case if you are interested, you can take this forward. Then this is for the lens. So if I change this distance gap and the gap of the lens or the waveguide feed, I can change my S parameters. So this is L equal to 0. So you get a resonance at much lower frequency. L equal to 2 is the best case where you get good resonance, right, with sufficient bandwidth. So this is used. So variation of L equal to 2 millimeter helps in impedance matching. So earlier you could see that the impedance matching was not very good. This was up to -8 dB only. What we require for impedance matching is -10 dB. So with the help of this lens, you are also achieving impedance matching. For L equal to 2, you get good impedance matching. So this is the fabricated structure. So we have 3 lenses, right, connected to 3 different parts, and then there is a waveguide cross section wherein you can feed power. So you can feed power at this point. You will get output at these 3 different cases. So the earlier antennas were printed antennas. So this is a waveguide based antenna. So this structure is machined in aluminum. So this was done in our workshop. This is fed by a WR19 waveguide cross section. So the dimensions of the waveguide here are 4.8 mm cross 2.4 mm. Then lens structure is integrated at the end of the 3 openings. So these are 3 openings. So now in this case, we will see this yellow colored lens. The earlier lens was a red colored lens. So slight change in the material. Therefore, the color has changed. So these are the scattering parameters. Measured is the blue curve, which lens, of course, and the black one is the simulated one. You get the slight misalignment, as you can appreciate. There are 2 parts. This part on top of this part. The 2 parts are put together, and that's how the antenna is fabricated. So while machining this, there may be small errors, so which has caused changes, a slight shift in the frequency. However, as far as the band is concerned, the band is similar, but it is shifted. So bandwidth of around 1.7 gigahertz is achieved. So this is a huge bandwidth. 1.7 gigahertz will be a huge bandwidth. This is E-field distribution. So from the lower side, you feed in, and the power goes in 3 different directions. Then there is lens here, which will enhance the gain. So this black outline that you see, these are for the lens. So as a result, you can see the simulated pattern here. So there is one beam along this direction, there is second beam along this direction, there is third beam along this direction. So this antenna essentially can be used for both on-body links and off-body links, because it radiates in a perpendicular direction as well as it radiates in the tangential direction. So you can see this. This is simulated and measured pattern. So they are closely matching. So 3 different beams are achieved. So because of the lens, the 3 beams are confined using the lens structure. The measured and simulated 2D radiation patterns. So 3 beam, the directions of the 3 beams are 0 degree, 87 degree, and 270 degree. So you get the beam in 3 different directions. So you can use this antenna for both on-body links as well as off-body links. Then this is a recent work wherein we have a dual mode antenna. So essentially there are two radiating structures. One is this patch antenna in the center, which is fed by a feed line on the other side, bottom side of the structure. So there are three layers: layer 1, layer 2, and layer 3. So this patch antenna is aperture coupled. So you can see in the ground there's a small opening. So this is called as an aperture. So this patch antenna is excited by this aperture, right? And this ring is excited by this feed line. Right? And this is a mid copper layer. So this is a common ground plane between the two. So this antenna can be used for on-body propagation in mode 1, off-body propagation in mode 2. Same antenna can be used for on-body propagation as well as off-body propagation. Then coaxially located patch and loop structure. Patch and loop are in the same plane. Loop is used for on-body communication and patch is used for off-body. Generally, it is known that patch antennas are broadside radiators. Therefore, it is used for off-body communication. Whereas this loop, right, it is along with this slotted ground is used for on-body, so end fire radiation. So these are the plots for S parameters, mode 1 and mode 2. So we have sufficient bandwidth in both the modes, and this is the coupling. So coupling is better than minus 35 dB. So dual mode operation in mode 1, you get 56.4 gigahertz, and in mode 2 it is 55.45 to 63 gigahertz. So both the bands, both the modes are possible in the same band with very good isolation, better than 35 dB. So the patterns are shown. Mode 1 for on-body communication. You can see these two patterns, these two peaks here, and this is for off-body communication, perpendicular. So this is the pattern. So same antenna can be used for off-body as well as on-body communication. So this is pattern for mode 1 at 58 gigahertz. So you can see that it is going towards two different directions. And this is for mode 2. So this is for off-body communication. So angular beamwidth here is 66.3 gigahertz, 3 degrees, whereas in this case the angular width was 13.4 and 14 degrees, so close to this. Beam directions are 64 degrees and 116 degrees. And so gain, this is the gain for this is simulated gain. We are yet to measure the gain. Simulated gain for mode 1 is up to 9.3 dBi. Whereas for mode 2, it is up to 7.81 dBi maximum gain. So by switching the elements, the mode of propagation can be easily changed, and as a result, you can either use the same antenna for off-body communications or for on-body communications. I think that is all I have for this talk. So these are some of the references that are used. So if there are any questions or queries, I'll be glad to answer.
Now I request participants to please ask your question. If you have any questions related to the session.
I don't see any questions in the chat box at least.
बरं, सातपुतेची गंमत सांगते हर्षला. तिला पाहायचं होतं की मी ऑनलाईन लेक्चर कशी घेते, कारण माझ्या नंतर तिचं लेक्चर होतं. बाई जवळजवळ 7-8 वेळेला आली. बरं आली तर मी माझं नेटवर्क यायचं ना, तर मी बाहेर.
Okay. So any questions from any participants? You can write.
Sir, can I ask?
Yes, ma'am.
Yeah, please.
Please, you can.
Sir, I'm Dr. Jayashree Kulkarni from Pune.
Okay.
Sir, I would like to know whether the normal connectors like SMA 10 type 11, are these connectors suitable for millimeter waves antennas? Because normally if I see the operating frequency is up to the 18 gigahertz.
Right.
So, yeah, please, if you could put insight on this connector, so
The
it will be.
yeah. So the normal connectors that are used, right, SMA connectors, they work up to 18 gigahertz only. Beyond that, you
Okay.
require a different type of connector. So there are 2.9 type of connectors. Then you have 1 mm connector, 1.85 mm connector. So at different frequencies, the frequency band, the connector has to be replaced. So normal the SMA connectors will work up maximum up to 18 gigahertz. So beyond that, they will be very lossy. So basically, they won't have 50 ohms as input impedance, as its impedance, characteristic impedance. So the impedance will be different, and it is very difficult to match because there will be a lot of losses.
Okay, sir. Thank you so much, sir. Thank you.
Okay.
Good afternoon, sir.
Yeah.
Sir, I am having a small doubt regarding to this one. While we are placing these wearable devices on the surface of human body,
Right.
so then we may consider the dielectric constant of the skin muscle like that. So, is there any specific dielectric constant? Is there a standard dielectric constant is there for the skin muscle, or how we can
Yeah.
take this
So,
up together?
yeah, basically, there's a lot of study on the dielectric spectroscopy of human body parts. So skin, then blood, tissues. So there's a lot of spectroscopy study. So you'll get these parameters in different ranges in the entire frequency band. So one has to pick up from those bands what is the dielectric constant, what is the real part, the imaginary part, and all those things. So there's a lot of data available in open literature about the parameters of various layers: skin layer, tissue layer, bones, blood, and all.
Yes, sir. Yes, sir.
So
Thank you. Thank you, sir.
depending on the frequency of your operation, there will be slight variations in the values.
Yes, sir. Yes, sir. Where we are placing, whether on hand or somewhat like that, so then it may be different.
Yes, the difference is also because of that, and also frequency. At what frequency you are operating, so that also makes a difference.
Okay, sir. Okay, sir. Thank you, sir. Thank you.
Okay.
Anybody else
Okay.
have a question? Any other participants has the question? Please ask the questions if you have. Otherwise, we can move to the concluding session. Yes, sir.
Yeah. Okay. I think there are no questions.
No questions are there. Thank you, sir. Thank you, wonderful, for your wonderful session.
Thank you. So sorry, I had to make changes in the schedule because I have a scheduled meeting at. It was actually unscheduled meeting, but I cannot postpone it. It is not in my hands, so I had to reschedule my talks. But I hope they were useful to the participants.
Yes.
And it did. I hope they also made the goals of your FDP program.
Yes. So now I request our HOD, Dr. A.S. Vibhute, sir, to propose vote of thanks. Vibhute, sir, are you there?
Thank you, all the participants. Specifically, I want to thank Abegaonkar sir for his wonderful sharing of thoughts on vital sign detection using radar on body antennas for body area network ban. I think whatever may be knowledge he has shared with us, that knowledge will be certainly helpful and will give research results for all the participants. And uh, I am very much thankful to him for extending the facilities available at IIT Delhi through Care Center. And certainly, I hope the many youngster researchers, they will avail this facility and they will be in touch with you, sir. And
Okay.
certainly we would like to extend our cooperation with you people so that such kind of technologies will be disseminated to the rural part of the India. So I'm very much thankful to you for your uh, wonderful knowledge sharing, as well as I am thankful to you for accepting our invitation and guiding us in this session. So thank you very much on behalf of Swiss College of Engineering. I am thankful to all the participants for attending the session 1, 2, and 3. So thank you very much. So for today, we'll be concluding this session here only. So tomorrow again, we'll meet at 10 o'clock with session number 2 by Dr. Vasudeva Behra, sir. Uh, so tomorrow sharp join at so that we can start the session sharp at 10 o'clock. Thank you very much, sir. Thank you, Abegaonkar, sir.
Thank you so much.
Thank you, sir.
Abegaonkar sir. Sir.